Dr. Ranjani Parthasarathy is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures in computer networks. We are looking at the TCP layer protocol. Today's lecture we will be looking at some details of the transport of this TCP layer protocol. We will be specifically trying to take a look at details of the adaptive flow control that is used in TCP and congestion control in TCP. As we know, transport layer protocols, when we talk of transport layer protocols in the internet, there are two flavors that we have, TCP and UDP. TCP is a reliable transport layer protocol and UDP is an unreliable protocol. Now TCP endeavors to enhance the services provided by the unreliable IP protocol using a number of techniques. Connection oriented approach is one of them, sequence numbers and ACKs, use of sequence numbers and ACKs is another, use of retransmissions, flow control and congestion control. So we have already looked at how connection is established in the state transition diagrams that are used for connection establishment and termination, and how sequence numbers and acknowledgements are used. So we now will take a look at how flow control and congestion control are handled in TCP. Before that, a quick look at the TCP segment format once again, just to recap what we have. So in terms of TCP flow control, there is one field here that is going to be used, which is the advertised window field. Now this will be the field that is used by TCP to indicate the size of the window that is to be used by the sender. So what is our TCP flow control problem as such? It is that you have a fast sender and a slow receiver. So the slow receiver must be able to tell the fast sender to not send data so quickly. So the flow control mechanism that is used by TCP is the following. It is the sliding window protocol. So a sliding window is the one that is used to make transmission more efficient as well as to control the flow of data, so the destination does not become overwhelmed with data. So this is our basic problem or the definition of the TCP flow control problem, and the solution is that we will use a sliding window protocol. So what are the details of this sliding window protocol as it is used in TCP? That is what we will look at now. Okay. So if you look at the TCP flow control mechanism, TCP sliding windows are byte oriented. That is, when we talk of windows here, we are not talking about frames or segments, but we talk about bytes of data that is being transmitted. So the window deals in terms of number of bytes that are to be transmitted. Second point is, each side specifies the sliding window size in every TCP packet using the advertised window field. Packet by packet you can vary the window size. That is the beauty of TCP, it allows you to adaptively change the window size. Third is, the sender's effective window is the amount of data he can send using the receiver's current advertised window size. So on a packet by packet basis, you are able to send information that can control the effective window size at the sender. This is the crux of the TCP flow control mechanism. Okay. So if you look at the receiver side buffer, let us look at what are the fields that we need to maintain. So let us look at what we have here. This is the entire received buffer that you have. Now from this buffer, your application is reading data. So the last byte read is indicated over here, and this is the amount of data that has been received, let us say, from the other side, and this is the next byte that is expected. So this part is empty, you can receive more bytes in the network here. This is the occupied part of the buffer, the pings part, and this part has already been consumed. Okay, once it has been consumed, it is also recycled and added to the empty part of the buffer. So now there are three things that we need to note over here. One is the last byte that has been read by the receiver application, the last byte that has been received by the TCP sides, the TCP on the receiver side, and this is the next byte that is expected. In fact, this next byte expected is the field that will be used to send the acknowledgement, saying that this is the field that I am now expecting to receive, byte number 200 in this case. So last byte received in this case is 199. Okay. So this is the information that would typically be there on the receiver side's buffer. Now the receiver throttles the sender by advertising a window size which is no larger than the amount that it can buffer. That is one thing. Second thing to remember is, on the TCP receiver side, the last byte received minus the last byte read should be less than or equal to the maximum receive buffer. This is basically to avoid your buffer overflow. You obviously cannot read more than you have received, right? So that is something to be remembered. Now, in terms of calculating the window size that is advertised by the receiver, so the TCP receiver advertises an advertised window which is calculated as follows. This is equal to maximum received buffer minus last byte received minus last byte read. That is the amount of free space that is available in the receiver's buffer. That is the value that is advertised by the TCP receiver. So this is what is the advertised window field, value that is put in the advertised window field, which is sent back by the receiver. Now, if you look at the sender side, if you look at the buffer on the sender side, right. So here, let's say this is the entire buffer that's available. Now, in this send buffer, the sender window size is determined by the receiver's advertised window. Let's say the advertised window is this big, the one that's colored in blue. Okay. Now, out of this, so up to this I might have already sent some data. So, let's say this is my last byte that has already been ACT, and I have already sent some amount of data. So, this is the last byte that is sent. So, the difference between these two is the amount of data that has been sent but has not yet been acknowledged from the receiver. So, last byte sent minus last byte ACT. So, the amount of data that I can further send is determined by this advertised window minus the amount that has already been sent but not yet been acknowledged. Okay. So, this part here would be my effective window size. So, this will give me the amount of data that I can send. Okay. So, this is how the sender side would calculate its effective window size. That is, you need to keep track of the last byte acknowledged, the last byte sent, the current advertised window size. So, as long as the current advertised window size is larger than this value over here, that whatever extra large, whatever extra portion is there, so much amount of data can further be sent. Okay. This is the point, this is what is actually done on the sender side. Okay. Now, so if you look at this formally in terms of how the advertised window is calculated based on these pointers, so the TCP sender must adhere to the advertised window from the receiver such that last byte sent minus last byte ACT is less than or equal to the advertised window. Now, remember, last byte sent minus last byte ACT is the amount of data that has not yet been acknowledged. The amount of data that has not yet been acknowledged will always have to be less than or equal to your advertised window size. Okay. So, if this value is already equal to your advertised window size, then it means that you cannot send any more data. Okay. So, the effective window that is to be calculated is as follows. So, we have to use the effective window, which is calculated as advertised window minus last byte sent minus last byte ACT, which is what we saw in this picture that we had just looked at earlier. Advertised window minus last byte sent minus last byte ACT. This is our effective window size. So, if you look at this picture here on the sender side, so let us say we have this scenario now, that is, this is the total size of the buffer. Byte numbers 200 to 202 have been sent but have not yet been acknowledged. All these have already been sent, okay, and this is empty. This can be to be filled by the application layer process. So, this part here is your occupied part of the buffer. Okay. Now, if the window size is equal to this, then sent, this part has been sent but not yet acknowledged. So, this is the next byte that is to be sent. So, this portion here from 203 to 211 can be sent immediately, because this is my entire window size, of which effective window size will be 203 to 211. Okay, just to take a look at a particular scenario, that is all. Now, you can also see how the window will slide as data is received. Similarly, the window will also expand and shrink as data is received as the effective window size varies. So, just take a look at that. So, if you look at the sliding window size, so let us say the receiver window is from 200 to 206, up to 202 has already been sent, and if this is the window size that you have, I can send 4 more bytes, 203 to 206. Okay. Now, if I receive the acknowledgements for 200 and 201, look at how the window, now how the entire window will slide. So, 203, 204 are yet to be acknowledged, but I can send these 203, 204, and I can send up to 209. So, from 205 up to 209 can now be sent. So, you can see that the window has slided based on the acknowledgements that are received. Now, next let us look at expanding and shrinking of the sender windows. This will depend on the size of the window size that I receive from the advertised window. Okay. So, if this is, so in this case you can see that I have a larger window that is advertised by the sender. So, if so many bytes have already been transmitted, I can still go ahead and transmit another 5 bytes. Okay. The window size here is 10. If the window size is smaller, so let us say the window size is only 6, then I have already transmitted 210 to 11, not yet acknowledged, so I can only transmit 4 more bytes, 212 to 215. Okay. So this is how you can see that the window size will be expanded and shrunk by the sender depending on the advertised window size. Okay. And the number of bytes that have been transmitted and the number of bytes that have been acknowledged. Okay. All these are taken into account. Okay. So if you look at summarily what the sender side flow control rules are, it would be as follows. One is you will first have to calculate the effective window size. So if the effective window is greater than 0, then the sender can send more data. If it is equal to 0, you cannot send any more data. Second is the last byte written minus the last byte acknowledged will have to be less than or equal to maximum send buffer. Okay. Now this is required because you cannot overflow the buffer, that is you cannot write more data into the buffer than it can hold, right. So you need to keep track of that. So TCP sender process must then block the sender application if the last byte written minus the last byte act is equal to the maximum send buffer. If it is equal to max send buffer, then which means that so much of data has not yet been acknowledged, right. So you cannot send any more, you cannot write any more data into the buffer. So you have to tell the application process that you cannot write any more data, stop writing more data, and you will allow it to write data only after you have sent data from the buffer. Okay, this is what is done on the sender side. Okay. So now we will take a look at how congestion control is done. So if you look at TCP's congestion control mechanism, now first of all we need to understand why congestion control is required by TCP, right. So it is congestion in the network which will lead to packet delays and losses. Whenever there is congestion in the network, now look at why congestion happens in the network. Whenever we have more number of data coming into the network than the network can handle, the network's capacity is being exceeded. So typically how will the network react to that? It will delay packets and it will lose packets. Okay. So congestion in the network basically leads to packet delays and losses. So what we need to do therefore is identify these packet delays and losses and try to make sure that you don't send so much of data into the network and thereby reduce the congestion in the network. Now what will happen from TCP side? Let us look at what happens from TCP side. Now from the side of TCP, whenever a packet delay or a packet loss occurs, it will cause TCP to time out. So a packet loss and delay in TCP is identified by TCP as timeout mechanisms. That is, it will have transmitted some data into the network. Now it is waiting for an acknowledgement to come back. If it does not receive an acknowledgement within a certain amount of time, then it will time out. It will set a timer for every packet that is transmitted and it will time out. So when a timeout occurs, TCP then knows that something has gone wrong in the network. Okay. So what TCP will do is it interprets these timeouts as indication of congestion. So this is how TCP tries to identify that congestion has occurred in the network. Remember, TCP is a protocol which is an end system, it is a host based protocol, right. So it has no information about the network directly. So it only estimates that it must be because of congestion in the network that it is losing packets. Okay. So TCP therefore uses this timeout, which could be caused by packet losses and packet delays, which could be caused by congestion, as the indication of congestion. So TCP interprets timeouts as indication of congestion, and once it finds that timeouts have started occurring, it knows it has to do something about congestion. So it will decrease the amount of data that it is sending into the network. Okay. So this is the basis of how TCP tries to do congestion control. So in terms of congestion control, as I said, let me just summarize these 4 points here. So congestion in the network leads to packet delays and losses. Packet loss and delays cause TCP to timeout. TCP interprets timeouts as an indication of congestion and decreases the amount of data sent into the network. So in terms of congestion control, we need to look at how this decreasing the amount of data sent into the network actually happens. Okay, so what does TCP do for that? What TCP does is it maintains another window called the congestion window. Now we just saw that for the purpose of flow control, it uses something called effective window, an advertised window which is sent by the receiver, and an effective window size is calculated, right. So if for doing congestion, what TCP for handling congestion or doing congestion control, what TCP does is it maintains yet another window called the congestion window. Okay, so let's look at how this congestion window is maintained. So this congestion window is just a variable that is held by the TCP source for each connection. Okay. So TCP now is modified such that the maximum number of bytes of unacknowledged data allowed is the minimum of congestion window and advertised window. Now we saw that normally we will not allow, with flow control, we will not allow to have more than advertised window amount of acknowledged data, of unacknowledged data. But now what we do is we calculate something called a max window, which is minimum of congestion window and advertised window. So if advertised window says 10 and congestion window says 5, then your max window actually would be determined by the minimum of the two, which is 5, which is actually based on the congestion window. Okay, we will come to how the congestion window is set a little shortly, but now just understand that I have one more factor here to consider, which is set based on congestion in the network, which is the congestion window. Okay, so we have congestion window comma advertised window. Take the minimum of these two values and set that as your window size. Now it is based on this that the effective number of bytes that can be transmitted in the network will have to be calculated. Now this congestion window size is adjusted according to three rules. There are three things that we use here. One is slow start, another is additive increase, and the other is called multiplicative decrease. In fact, these two are normally combined together and referred to as additive increase multiplicative decrease technique, or the AIMD technique. Okay, additive increase multiplicative decrease. Okay, so let's take a look at how slow start and the AIMD mechanisms work. When we do slow start, that is when a new connection is established, we really do not know if there is congestion in the network or not. Okay, so if you just went ahead and transmitted a whole lot of data because your advertised window size was very large, what could happen is that if the network was already congested, then you're directly transmitting so many bytes of data into the network would only lead to loss of data. So you want to avoid that. So what we do is we start slow, right? So what we do is we start with a congestion window size of 1 MSS. Now remember, our 1 MSS is the maximum segment size that you will have in TCP. Now TCP normally has a maximum size that it can have. So you can only send 1 MSS amount of data as a single segment. Okay. So now what you do is your congestion window initially is set to 1 MSS. So 1 maximum size segment. So if the sender side TCP has 1 MSS amount of data to send, right, or even if it has more than 1 MSS amount of data to send, it first starts with sending only 1 MSS of data, because remember our effective window size is determined by your congestion window as well as your advertised window. Even if advertised window said you can send 10 MSS of data, you will start with a congestion window size of 1. So I'll just go ahead and send 1 MSS of data. So this picture here on the right will tell you how the congestion control slow start mechanism basically works. So I will set this congestion window to 1 MSS, so I will send 1 segment of data. Okay. Now each time I get back an acknowledgement for 1 segment of data, what I now do is I add 1 to the congestion window. So what I do here, I sent 1, my congestion window size is 1, now I got back 1 acknowledgement for that. As soon as I get back an acknowledgement, my window size now is made to 1 plus 1, 2, and now I can go ahead and send 2 segments of data. So I send 2 segments. Now what happens is I will get back acknowledgement for both these segments, and as I get 2 acknowledgements, I add 2 to this congestion window. So the congestion window size now will become 2 plus 2, 4. Okay. Now I can send 4 segments of data. So on sending 4 segments for data, I can get back 4 acknowledgements, assuming that no losses are there in the network, right? That is, there is no congestion in the network, so everything is going fine. So I get back 4 acknowledgements. So now my window size becomes, it was already 4, I get back 4 acknowledgements. For every ACK I add 1, so I get 4 plus 4, 8. So I can now go ahead and send 8 segments of data into the network. Okay. So what we are actually doing here is, you are starting slow, you are starting with only 1 MSS of data, but you are doubling up, actually you are doubling up quite fast, right. So the name slow start basically comes from the fact that you are not actually transmitting the entire advertised window amount of data, but you are starting with 1 and slowly building up. Okay. So 1, then 2, then 4, then 8. Okay. So this is how the data is transmitted. So each time a frame is acknowledged, we are adding 1 to the congestion window and you are increasing the congestion window. Now, so you will keep on repeating this. How long do we do this? So you repeat this until either the congestion window becomes greater than or equal to something called a congestion threshold. Now I will just shortly tell you what this threshold value is, or a timeout occurs waiting for an acknowledgement to come. That is, say for instance I have now transmitted 8 segments of data. Now if this is a situation where congestion actually is there in the network, then I may not, a packet may be lost or packet may be delayed, in which case I don't get back an acknowledgement, and therefore a timeout will occur. So when a timeout occurs, I know that yes, probably this is congestion that is there in the network, so I have to do something about it. I can't just go on doubling up as I did in the case of slow start, but now I have to reduce the amount of data that is being sent into the network. Okay, that is what we do. Now this congestion threshold that we talked about just now, okay, that is initially set to maximum TCP window. Okay, this is a value that is set as the initial value. Now what we do is, if the congestion window becomes greater than or equal to the congestion threshold, okay, now you start using additive increase. That is, once I have identified a situation where I can't go on just doubling the amount of data I am sending into the network because either a timeout has occurred or a congestion threshold has been reached. Now what I do is, I start increasing the congestion window size in an additive manner. Now remember that in slow start what we were doing is, congestion window was doubling for every set of transmissions. It was 1, then it became 2, then 4, then 8. Now what we do is, the moment we find that there is congestion in the network, we won't double the size, but we will increase it additively. That is, if the window size was 8, right, then I can make it 9, then I can make it 10, 11 and so on. Okay, so that is what we do in the additive increase phase. So that is the next phase. So let us look at how this additive increase works. In additive increase, you gradually increase the window size in order to discover the optimal size. That is the idea. That is, whenever congestion occurs, typically what you will do is, you will decrease the window size and slowly you will start increasing the window size. Okay. So let us say for instance, in this case, let us take a situation where I went on doing slow start and I reached the congestion threshold, not a timeout but a congestion threshold. So once I reach the congestion threshold, now I know that I should not start sending too much of data into the network, but slowly I can increase the data. So I go into a phase called additive increase phase. So now in additive increase phase, look at what we will do. We will slowly, gradually increase the amount of data sent to the network. So for instance, in this example, I am actually starting with a value of 1. It could be any other value as well. So suppose I started with a value of 1. When I get back 1 acknowledgement, I now make it as 1 plus 1, 2. So far so good. Okay. When I send 2 packets, now for both these acknowledgements put together, right, for this entire window size, for the entire window size, I add 1 to the receiver. That is, when I get an acknowledgement of the entire window of packets that I have sent, now I add 1 to the congestion window size. So my congestion window now, which was 2, becomes 3 on receiving these 2 acknowledgements. Okay. So we increase congestion window by 1 MSS each time the entire congestion window is acknowledged. Okay. So now I have sent 3 packets. When I get back 3 acknowledgements, I again increment it by 1. So from 3 it becomes 4. So this is the additive increase phase. Okay. So the implementation of additive increase is very simple. So each time an ACK is received, you set the congestion window as equal to congestion window plus 1 MSS into MSS by congestion window. Okay. So this is how we do it, because remember we are doing everything in terms of number of bytes. So we need to do this thing in terms of 1 MSS amount of bytes into MSS divided by congestion window. Okay. Now coming to the multiplicative decrease part. So whenever a frame is dropped, that is, a frame is lost and frame or segment is dropped or lost and a timeout has occurred, now you will cut the congestion window into half. So the congestion window will now become congestion window by 2. If the congestion window was 8 and I found that a timeout has occurred, then my congestion window will be set to congestion window by 2, which will become 4. Okay. Now how does the TCP know when a frame is dropped? As I said, it gets a timeout waiting for an ACK, or it gets too many duplicate acknowledgements. Okay. Now what do we mean by this? Suppose let us say I transmitted packets 4, 5, 6 and 7. Packet number 4 let us say was lost, but 5, 6, 7 packets were received correctly on the other side. Now I will get back an acknowledgement for 5, 6 and 7, but all the acknowledgements will say that I am waiting for packet number 5. So all these 3 are duplicate acknowledgements. Now the fact that duplicate acknowledgements are being sent indicates to the sender that actually something is being received, right. So it is not congestion in the network, but only one packet was lost. So this is an indication that packets are actually reaching there, but one packet has been dropped. Okay. So this can be one indication, or a timeout occurs waiting for an acknowledgement. You do not receive an acknowledgement at all. In both these cases, you know that packets are being dropped. Okay. So in these cases, you will go in for this multiplicative decrease phase and decrease the congestion window size by 2. Okay. So now the question is, why do we do multiplicative decrease? Why not something like an additive or a subtractive decrease? Okay. So what do we mean by that? I said that if I transmitted 8 packets and an error had occurred, now with multiplicative decrease I will set my congestion window to 4. After I have set it to 4, now I sent 4 packets into the network. Now what do I do? If I start getting back acknowledgements correctly, I will now increase the window size by 1. That is, I will keep doing additive increase and multiplicative decrease. Okay. Now the question is, why should I use this multiplicative decrease? Why not use additive increase? Okay. So additive increase and multiplicative decrease are both a necessary condition for stability. Okay. So that is what I have indicated here as an important point to remember. So why do we use multiplicative decrease and why not use additive decrease? The reason is, from 8 why should I bring it to 4 and not just bring it to 7 or 6? We are decreasing a lot, so that we first want to make sure that you are not unnecessarily sending more and more data into the network. First decrease, okay, be very sure that you are not going to cause more traffic into the network. So the moment you find that there is congestion in the network, do a decrease and make it a multiplicative decrease. Okay, so if you do multiplicative decrease, you are drastically reducing the amount of data, and then slowly you start increasing the data. Why can't I use multiplicative increase in this case? Again, because you do not want to have a situation where you just decrease the data, so congestion was reduced, again you start increasing the data, again congestion occurs. You do not want that kind of a situation. So we go in for an additive increase and a multiplicative decrease mechanism. So this additive increase, multiplicative decrease, we say is the necessary condition for stability. So otherwise you will keep having variations in your data transfer. So to avoid that, we do additive increase, multiplicative decrease. So with additive increase, multiplicative decrease and slow start, congestion is effectively handled by TCP. So we'll just take a look at this picture which just shows these situations. Okay. So you can see the data transfer that's happening here. So let's say I started off with a slow start initially. I would transmit 1, congestion window size would be 1. I transmit 1 packet, receive acknowledgement for that, and then I transmit 2 packets, right. Now I receive acknowledgement for these 2, so my window size becomes 4. I transmit 4 packets. Now let's say on receiving this 4, my window size becomes 8, but when I transmit with 8 packets, let's assume that there was congestion in the network and the timeout occurred. Okay. So if a timeout occurs, what do? Now I know that I cannot be transmitting the same amount of packets to the network. So it's a long timeout that has occurred. So what I'll do now is I'll come back to 1 again, set my window size back to 1 and do a slow start until I reach the congestion threshold. Okay, this is a very unique situation. That is, this is used whenever a long timeout occurs. That is, you will start again with slow start until congestion threshold is reached. But once you reach congestion threshold, then you start doing additive increase, right? Start doing additive increase and keep doing additive increase until again a congestion occurs and a timeout occurs. Okay, this is what we do. And you can see how the congestion window size is varying also over here. You can see that it is exponentially increasing, then it's set to 1 again, and then it increases again an exponential increase, and then it increases linearly. Okay, this is what we see over here. Okay, so to summarize what we have looked at so far in today's class is basically details of the flow control and the congestion control mechanisms of TCP. So we have seen how the window sizes are calculated at the sender side on the receiver side, and we have also looked at how timeouts and windows are used to handle congestion. Okay. So in congestion we looked at these 3 mechanisms of slow start, additive increase and multiplicative decrease. Okay. Questions again for a quick review of the topics covered today. Question number 1, what kind of flow control mechanism is used in TCP? Question number 2, how is the effective window size calculated? Question number 3, how is the advertised window size calculated? Question number 4, what is congestion window? Question number 5, what is meant by slow start? Question number 6, why is AIMD used? That is additive increase, multiplicative decrease used. Thank you.